to everyone. Happy to be giving this talk. Well, let me see if I. Oh yes, I can. Yes. Okay, this is just a summary, so you will see the summary on top in the end. I'm happy to have been member of the School of Mathematics and Physics, Lincoln, for most of its history, 8 years out of 10. So I started just 1 year after the beginning. So actually, the year when we started giving lectures, actually, the first year we had students, and left a little shorter than a year ago, basically moving to a better climate for me. And yes, and well, again, he was a wonderful colleague, and I wish him the best for his retirement. Well, this is what I'm going to talk about. Much of it is old material. This is a sort of recap of co-class theory, and I'm really not much qualified to talk about co-class theory in the presence of Charles, who reminded us yesterday. And okay, now we talk of co-class theory, but if you go back 14 years, it was conjectures. These 5 conjectures of Charles and Mike Newman, and eventually they were all proved. And for me, for the purpose of this talk, being able to build a co-class theory is based on, or the main point is, the objects you are studying are soluble. So this is my simple view of co-class theory. To get started, you need to know that property groups of finite co-class are soluble, which of course we are really talking about the infinite property groups, so the infinite dimensional things. Soon after those years, so soon after the conjectures were proved, some people started to investigate Lie algebras to see how much of this can be transferred to Lie algebra. So is a co-class theory for Lie algebras possible? So I will only talk about graded Lie algebras. So, and when I say graded Lie algebras, I mean graded over the positive integers. So they will have grading like that displayed, and so it's a direct decomposition as vector space, and grading means that the Lie product of the components Li and Lj are contained in Li plus j. Any characteristic, any field for the moment. And the co-class of a graded Lie algebra is defined in a completely analogous way as for property groups. Here the notation, so when I'm writing the quotient of L by L to the I, L to the I stands for the I power of L. So in the context of Lie algebras, that's the lower central series of the Lie algebra, but it can simply be expressed. Those terms can be simply written as Lie powers. Okay, so I use lower indices for the grading and upper indices for the Lie powers. Having finite co-class in the infinite dimensional case simply means that the quotients of that, the consecutive quotients of that lower central series have dimension 1 from some point on. And the smallest co-class is co-class 1, the smallest value of the co-class. And in that case, we talk about algebras of maximal class, like we would do for groups. And I will abbreviate throughout the talk that as GLAMC, so graded Lie algebras of maximal class. And okay. So an attempt to co-class theory for Lie algebras, for graded Lie algebras, was started by Shalev and Zelmanov in a paper of 1987 under these assumptions. So we assume our graded Lie algebra first in characteristic 0. Lie algebra of finite co-class over a field of characteristic 0, and also generated by its first homogeneous component, L1. And both of these hypotheses will turn out to be essential. Assuming that L is generated by its first homogeneous component, or by L1, comes quite naturally if one comes from the world of group theory, because much of the Lie theory approach to groups, or to finite or profinite groups, is building graded Lie algebra out of some filtration of your group, be it the lower central series or lower central or p-dimension series, and the graded Lie algebra which you obtain in those ways are naturally generated by the first homogeneous component. So this hypothesis sort of mimics what should be natural coming from groups. And so they established that under this hypothesis, L has an important ideal of codimension 1, and as a consequence, L is soluble. So L is soluble, as I said earlier, is really the starting point of a co-class theory, and then they obtain further results, more precise results. If you compare with propy groups of finite co-class, the result for Lie algebras is actually much stronger. We are saying L has an important ideal of codimension 1. And then there is a third statement there, which it will be useful for me later. So if L is just infinite, then L is isomorphic to that M, which I haven't mentioned, but that's the example on top. So basically you start with a countably dimensional vector space as an abelian Lie algebra, and then extend it with a derivation Z on top, which simply, in its joint action, sends each basis element EI to the next one. So that's a metabelian. And basically, that's the only just infinite Lie algebra in this context. It is a Lie algebra of maximal class. It was known much earlier that the only graded Lie algebra of maximal class, infinite dimensional in characteristic 0, is that one. But this statement is stronger. The hypothesis is just that if L is just infinite. So again, this is much stronger than what happens with propy groups. If you dispense with the hypothesis, or rather, well, if you go to positive characteristic instead of characteristic 0, then you immediately have failure of co-class theory, in the sense that you have failure of solubility. And this was shown by Shalev, who constructed over any, well, you could say over any field of prime characteristic, but really it's enough to do it over the prime field, so the field of p elements. You can construct countably many insoluble or non-soluble graded Lie algebras generated by the first homogeneous component. So this is enough start for Cook-class theory, if you like. He built them out of certain finite dimensional simple Lie algebras, and because of this construction, his algebras have some kind of periodic structure. I'm not going to explain what I mean by periodic. Solubility would imply periodicity, but periodicity is obviously more general. Sorry, I think I skipped something. Yes. Okay. The situation. So shall I produce these algebras and show that they are insoluble? And in this paper with Andrea Caranti and Mike Newman, we showed that the situation of the landscape is actually much more complex than just this. Again, we are looking at graded Lie algebras of maximal class, infinite dimensional, over a field of positive characteristic, under the assumption that they are generated by the first homogeneous component L1. And the main result is that you get really many. So the number of isomorphism types is cardinality of the field to the exponent Aleph naught. So as many as the infinite sequences of elements of the field. That's good. And well, most of them are not soluble, and they are not even periodic. Just because there are so many, they cannot be all periodic. So you could view it like that. And the way we get so many is that, okay, there are some constructions that you have one of these graded Lie algebras of maximal class, and then there are some constructions to produce a new one. And these procedures, these constructions, you can repeat them infinitely, countably many times, and you can take some limit, and that's how you get so many. So this is sort of okay. Andrea Caranti and Mike Newman, well, 3 years later, managed to show that these constructions are able to produce every infinite dimensional graded Lie algebra of maximal class generated by L1. So this forms a sort of classification of those Lie algebras. Okay, the classification in the sense that, okay, every object that you're trying to classify is there in your description, and then the isomorphism problem, the isomorphism part of the classification is not really an issue here. It's easy to distinguish two of them if they're isomorphic or not. That's not a problem. So this is a classification in the sense that it covers them all. It's a bit of an unusual classification, unconventional, because it's not just a list. It's there are some procedures we gave some procedures which eventually are able to produce them all. And that this was completed by Giuseppe Jurman, a student of Andrea, for characteristic 2, which has some complications, but it's not much different. Next, let's look at so what I've told you is, what if we go to positive characteristic? Now we go back to characteristic 0 and try to change the other hypothesis in the result of Scholeffer and Zellmanov, which was that the algebra is generated by the first homogeneous component. And if we drop that assumption, then again we get problems to build a co-class theory because we have insoluble objects. And one is the Witt algebra described in this example. So you take the derivation algebra of a polynomial ring. Okay, the standard derivation with respect to x would have degree -1. So you don't take the whole the algebra, which would be simple, but you drop the element of degree -1 and the element of degree 0 and take only the elements of positive degree. So that's the positive part. And that's not soluble. That's not soluble. Well, being soluble just means in these situations would mean to have a non-zero abelian ideal. But you know, if you look at the multiplication, if you look at the Lie bracket, Lie product, you can get non-zero Lie product by taking j and I as high as you want. So you will never get an abelian idea. So this is not soluble. And it's a graded Lie algebra of maximal class, and it is generated by E1 and E2 and E2. So the component of degree 1 and the component of degree 2. And the other part in Chalet and Delmanov's paper, well, the title was a co-class theory. I talked about that before, and the characterization of the Witt algebra. The second part is essentially this theorem. There are only very few infinite-dimensional graded Lie algebras of characteristic 0 generated by the first and second homogeneous component, and they have to be either this Witt algebra, which is insoluble, or the metabelian algebra M, which I showed you earlier, or another one. Okay, so these are soluble, but W is not. When I write that L is generated by L1, L2, we do not mean that necessarily those two are essential. I mean, that includes the situation in which L is generated by L1 alone. Okay? But we are talking about a graded Lie algebra of maximal class. So that would be generated by two elements, and you can always assume that those two elements are homogeneous. So each of those generators will have a degree, and so basically there are two alternatives. Or either the two generators have each degree 1, and so they span L1, or one of them has degree 1 and the other one has degree 2. That's the other situation. And then, well, if both of them have degree 2, well, then each component, then the Lie algebra has only the even components. You just rescale the degree and come back to the previous situation. So that assumption is really gives you these two alternatives. We are looking at a graded Lie algebra of maximal class generated either by two elements of degree 1 or by an element of degree 1 and one of degree 2. Just a quick recap of what we have seen so far. So with these two assumptions on generation, so degrees of the generators and the characteristic, here are the four combinations. So if your algebra, okay, it's a long sentence, graded Lie algebra of maximal class, it's generated in degree 1, so by L1, and in characteristic 0, then you get only one Lie algebra. This was known much earlier. If you assume it generated by L1, but in positive characteristic, situation looks complicated, but there is a classification by Andrea Carrenti and Mike Newman. If you only assume it generated by L1 and L2, but in characteristic 0, Then Shalep and Delmonov provided a classification with only, that's a simple classification with only few cases. And the remaining case, I have said nothing so far, and that's where I'm going to focus in the next section. So I will, roughly speaking, so we have a grade in the algebra of maximal class. So far, so it has two generators, homogeneous, so each of them has a degree. And I said either both generators have degree 1, and then I will speak about an algebra of type 1. In the next slide, I will consider the other case. That could be an algebra of type 2, where generator has degree 1 and the generator has degree 2. Or more generally, I can look at algebras of type n, where one generator has type 1 and the other generator has type n. So algebras of type 1 is just the assumptions are that it is generated by L1. So both generators have degree 1. So that means that L1 is two-dimensional, and all the following components will be one-dimensional. I'm assuming all algebras to be infinite dimensional for simplicity from now on. Okay, so we are in this situation. And then we need a further assumption. I'm making a further assumption here that in the algebra, in L1, there is one non-zero, at least one non-zero self-centralizing element, Z. That is not really, I mean, if it is there, good. If it is not there, you just you possibly extend the field of the base field of the algebra, and then you get it. So it's not really a big assumption. So why do I want this Z? Well, I want this element Z such that it's a joint action, since a sequence maps the remaining basis elements each to the next, as I wrote down here. Okay, so the first homogeneous component L1 will be spanned by Z and E1, and then you can define E2 and A3 and so on by the action of Z, and you get a graded basis for L. Something which is going to be important at some point is this sequence. So the multiplication of the structure of the algebra will be completely determined once you know the action of a set of generators on the elements of a basis, because then you can use the Jacobi identity to recover any other product. And so our generators here are, one generator is Z, and which has a very easy adjoint action on the basis. It just maps EI to EI plus 1 and so on. So you only need to know or to specify the adjoint action of the other generator, E1, and that's given by that sequence. Okay, so that sequence determines the algebra completely. And another important thing is that, well, you can have some freedom the choice of these generators, and you can always make sure that your sequence starts with a 0. That will be important. So this is an algebra of type 1. An algebra, next, an algebra of type n greater than 1. Okay, I told you roughly it is graded the algebra of maximal class, where one generator has degree 1 and one generator has degree n. This is a bit more general than the definition, the more specific definition which I have written here. So it catches too much stuff. So the right definition to give is the one which I have written here. So your algebra will be generated by an element z of degree 1 and one element of degree n. And then you need the adjoint action of z to map each Li onto the next homogeneous component. And if you write it this way, well, it will be automatically an algebra of maximal class. Okay, so the difference with type 1 is that in type 1, L1 is two-dimensional. Okay, so you have more freedom in the choice of generators. But in type n greater than 1, well, you have no freedom. You have your generator Z and then the element n in this case. In this case, all homogeneous components will be one-dimensional, except for possibly a few components that are zero, like L2, L3 will be 0 up to Ln minus 1, and then Ln, where your second generator lies, will be one-dimensional, and so will be all the following homogeneous components. So again, you can define a graded basis in the natural way, this way, and you will have a sequence of coefficients which completely describes your Lie algebra. One important fact is that there is one easy way of building algebras of type n out of algebras of type 1. You just keep the element z as generator, and you drop your other generator E1, and you possibly drop E2 and E3 and so on, and just keep En. So the subalgebra generated by Z and En will automatically be an algebra of type n. And then the question is, okay, can we go back? So if I'm given an algebra of type n, is this a subalgebra of an algebra of type 1? Well, maybe not always, but it will turn out to be that way in most cases, apart from some exceptions. So you can think of it like, okay, I have my algebra of type 1, but I don't see it all. I just see it as a subalgebra, which is an algebra of type n. How far can I recover the algebra of type 1? Let me see the time. Okay. So Andrea Caranti and Michael Vorley had some results on algebras of type 2. So again, generator of degree 1 and the generator of degree 2. And we have two results depending on the characteristic. If the characteristic is at least 5, so then any algebra of type 2 is either it comes from an algebra of type 1, or belongs to a countable family of exceptions, and these are all soluble algebras. So this sort of confirms what I said. Most algebras of type 2 come from algebras of type 1 by taking subalgebras, apart from these exceptions. And then they had a similar result. I mean, they also dealt with the case of characteristic 3, but it's more complicated. There is one additional family of algebras, and which can be much bigger because it's parameterized by the base field F, so it doesn't have to be countable, or it's of different nature. In what I'm going to say, because the idea is try to generalize these results to algebras of type n, and this case of characteristic 3, this situation will be avoided by assuming that the type and the characteristic, so in this case 2 and p, are not too close. They could be equal, but if they are not equal, they cannot be too close. Then they had another result, again on algebras of type 2, but in characteristic 2. And this looks a little bit looks a bit different. Again, any such algebra is either comes from an algebra of type 1 by taking a subalgebra, or by doing that and taking a translate of it. So here we don't have any exceptional family, but we have the necessity of taking these translates. What do the translates mean? Well, an algebra, you have an algebra L of type P, then you will have, it will be described completely by its sequence, this sequence of scalars. And you just add constant to the sequence. So you add the same scalar delta to every element of the sequence. And you can show that this is, again, the sequence of another algebra of type P. Okay. And the reason why it works is that, well, because the pth power of a derivation, characteristic P, is again a derivation. This is something which would not work for you took just the nth power. So the these translates only make sense when the type equals the characteristic, but give you a way of completing this, obtaining this classification. Okay. Okay. Recap. We have algebras of type 2 are classified. The results of well, in characteristic 0, they were classified by Shelef and Zermanov, and then Andrea, Caranti, and Michael only did the case of positive characteristic. And most of them are subalgebras of algebras of type 1. When or some exceptional family in odd characteristic, or those translates in characteristic 2. And the next, the goal is generalize all these to type N instead of type 2. And essentially, we want to show that most algebras of type N come from algebras of type 1 by taking subalgebras, or possibly taking translates when N equals P. So there will be two cases, either N equals P, so we study algebras of prime type P, characteristic P, or we want the characteristic to be larger than the type N, and quite a bit larger to avoid the exceptions which came up earlier. Okay, and this is the work. I don't have much time to talk about the work, but so 3 of my PhD students worked on this. Well, Simone Ugolini in Trento was actually a joint student with jointly supervised by myself and by Andrea Taranti, and then Claudio was my PhD student again in Trento, and years later Valentina Iusa was a joint student of Evgeny and me, and so she first worked on topics of where Evgeny was an expert, and then at the end she had a few months left and worked on these things. So these results are very old, but were published only relatively recently, 2021 and 2022. And part of the reasons is that okay, they did, Simone and Claudio, they did prove those classifications, but they were a big mess to read, very complicated, not really easy to I mean, really complicated. So a lot of work, later work with myself, went into clarifying those proofs, making them simpler, devising some tools to improve them. And these are the results. Okay, so let's look at the case n equals p, or p equals n first. And here's the compact statement, okay, rough statement, if you like, of a classification. So every algebra L of type P, under those conditions, so we are assuming odd characteristic P. Well, the case P equals 2 was that covered by Andrea Carranti, Michael V, so we can leave that out or compare it later. And then we have this other assumption, L, this letter L greater than 4P. I will tell you in a minute what that is. So under those assumptions, every such algebra L of type P is either subalgebra of an algebra of type 1, or translate of that, or it belongs to a countable family of exceptions that are soluble algebras. So this is similar to the result of Carranti and Volney, except that there was no exceptional families in that result, because when P equals 2, the family is empty. And you will, if I get to that point, if I have 5 minutes, you will see that that family will have bunches of P minus 2 elements, and when P equals 2, that's just empty. What is L? L is the length of the first constituent. Oh, what does it mean? That hypothesis, L greater than 4P, means that. So we need to assume that the largest metabelian quotient of L is well, large enough, quantified like that. We need L to have sufficiently large metabelian quotient to be able to proceed. Y constituent? Well, I think I'll try to say this as briefly, as quickly as possible. I told you about the sequence. So each of these algebras will have associated this sequence. This is just part of the multiplication table. It just describes the action of the element, the adjoint action of the element En. And in the special case, let's do the special case of the algebras of type 1. The sequence starts with a 0, and then there is some non-zero element, beta L1 there, and then there will be another bunch of zeros, and then a non-zero element, and so on. And we subdivide this sequence into blocks, which are made of zeros and end each with a non-zero element. And these are the constituents. And the number of entries are just their lengths. And you can generalize these to algebras of type n rather than type 1. It's just a bit more, well, there are some complications. So you may have a final block of n possibly non-zero entries, but just possibly non-zero, which creates some complication. And some ambiguities in the definition of the constituents length, which were resolved eventually. But for example, in the thesis of Claudio, he used one definition, and in the final publication, we used another one because it works more smoothly. These numbers, the constituent lengths, have some structural interpretation. which we didn't point out in our initial work with Andrea and Mike Newman, because it was not really necessary there, but it's more important here. And basically, these numbers, these constituent lengths, are the successive codimensions of the quotients of the lower central series, not of L itself, but of the commutators of algebra L. Okay. And in particular, the first one, which is the most important, this L or L1, relates to the dimension of the largest metabelian quotient of L. Okay. Well, you need to add this n to make things work smoothly, but basically it relates to the largest metabelian quotient of L. How much time? Well, okay, I think I can go quickly through the rest. So there was, okay, some information about the length of the first constituent is important. I mean, you cannot do anything, you cannot study these algebras. I mean, this is the first parameter of an algebra of maximal class is the length of the first constituent. And then you can move from there. For algebras of type 1, that number is twice the power of P, twice the power of the characteristic. In these papers, we proved, we generalized this result. We had to generalize this result to algebras of type n. So this theorem, as I have written it here on the slide, combines n could be smaller than p, or n could be equal p, combines both cases, and the formulation is the same. Again, under this technical assumption, L greater than 4p, you need enough zeros at the beginning, something like that. Then the length of the first constituent is, first of all, it is even, but that's an easy fact. That's the easiest fact to show. And then it is either equal to twice the power of p, like algebras of type 1, or there are some other cases. It lies between q and q plus n. So these are like this third point here. It looks like there are n cases and possibilities for L. Well, you could say no, because L must be even. Okay, but some of these, so that is about n half possibilities, but then each of them might correspond to two algebras. Anyway, in the final classification, the length of the first constituent, this number which we have just studied, will allow you to decide in which of the cases of the classification you fall. And here is so this is the theorem. Okay, sorry, I think my time is up, but I think I can finish it just reading it quickly. This is the same theorem I showed you earlier, written in a more precise form. So this is a classification of algebras of type P, where P is the characteristic. Then you look at the length of the first constituent, and then you get from that which case you are. So if L equals twice the power of Q, then your algebra L is a subalgebra of an algebra of type 1. If L equals Q plus P, so the rightmost, the extreme, on the right side of this interval of exceptions, then if you take a suitable translate of L, then you get a subalgebra of an algebra of type 1. And the remaining cases belong to some family of exceptions. And this family, for a given Q, you have P minus 2 algebras, and you can, there's an explicit construction of them. They were originally constructed as matrices. It was, Claudio's original thesis was quite complicated, very long, but we found a better construction as the algebras of derivations of algebras of divided powers, which is an important tool in the theory of modular, simple modular algebras. Okay, still another minute just to state the other result, which is concerns algebras of type n smaller than p. And considerably smaller than p to make things work. So you need p greater than 4n, so the characteristic greater than 4 times the type of the algebra. Then those algebras, well, then you have only 2 cases. So if L equals 2Q, twice the power of P, then L is a subalgebra of an algebra of type 1. And in all the other cases, all the other cases are explicitly describable exceptions that are soluble and countable in number. And he specialized correctly to the results of Andrea Caranti and Michael Fonli. Okay, that's all.